Hello everyone, and welcome to the lecture 1C. So here we will construct formal topological semi-classical quantum mechanics. So first let's start with formal semi-classical propagators. Let's assume that M, so we dealt with special symplectic manifolds, cotangent bundles to Q, cotangent bundles to Rn. So now let's consider M that is any exact symplectic manifold. Actually, the exactness is not a restriction. We can consider general symplectic manifolds. So then we'll discuss it later. In this case, so when alpha is not a one form, it is a connection, and omega is its curvature. And in this case, whatever ingredients we'll have, they will not be functions, but they will be sections of so-called formal pre-quantization line bundle. Okay, so this is, we don't need this. So now let's assume that we have two Lagrangian fibrations. In other words, we have two classical integrable systems. And given this geometric data, let's define a formal semi-classical transition amplitude. It's a formal version of what we discussed before as a semi-classical limit of the existing amplitudes, but now we just define it from the scratch. As follows. It's just the same expression as before. All ingredients as we had, so same as in lecture 1. Sorry, lecture 1a. Except, so here the symplectic manifold is not T star of Q, but it's just any manifold. So everything is the same. Alpha doesn't have to be PDQ. Now, just as before, this expression A doesn't depend on continuous deformations of gamma 1 and gamma 2. Now, if Bohr-Sommerfeld conditions hold, then it doesn't depend on topological classes of gamma 1 and gamma 2. But for the time being, we'll just assume that B are not quantized in the sense of Bohr-Sommerfeld. So just as we observed before, this expression is not a function in B1 and B2 because it doesn't transform this way. It doesn't transform this way because we have the square root of the matrix of the second derivatives. But, you know, with some technical setup that's explained here, we can see that actually it's a half density. So this expression that we had before, so what we can do is just for technical convenience consider a small neighborhood U in M of the intersection point of L1 and E2. Intersection point, this is our reference intersection point. And let U1 and U2 be the projections. So this is our U. It projects to U1, U2, pi 1, pi 2. So then here we have the unique intersection point A. And let's denote psi 1, psi 2 U, the restriction of this half density to U1 cross U2, and then it's clear that it's a half density and it's just an element of this space. So we will consider these formal transition amplitudes as the kernel of a formal integral operator, and let's just assume that f is an analytic function on U2 such that for each intersection point this function has unique critical point in B, unique critical point at beta 2 when B1 is in U1. All these assumptions are simply here because the number of critical points can vary when we vary B1 and B2. And then this sum will be a little bit problematic because, in this space we vary the arguments. And so all these assumptions about U1, U2, U, they're all just assumptions to stabilize the number of critical points and to identify the critical points for various values of B1. Okay, so if we will do this, we have a formal integral operator. Our transition amplitudes, the formal integral operator, exactly what we want, because the transition amplitudes, they are transition amplitudes. So they are transition from one basis to the other. So from this space to this space. And when we apply it to some element of this form, this is just the integral, formal integral over U2 of the product of this half density and this half density in B2. So we can write it as this expression, sum over the intersection points, and then with all our assumptions, if we vary B1, the number of intersection points will be the same, and if we vary continuously, we can sort of trace these critical points where they will go. So, okay, so this is the formal transition amplitude as an integral, as a formal integral operator. Okay. So now let's look at the semi-group property for formal semiclassical propagators. So it's a relatively simple exercise to check that if you take the composition of two transition amplitudes as a formal integral, if this would be integral operators, you would just take the integral over B2, but because this is whole formal setting, so we take the formal integral. And formal integral, as you remember, this is basically, collection of differential operators. This is not really an integration. Okay, so what I will not discuss here is this Maslov corrections that may appear here. Okay, the conjecture. So now remember that the transition amplitudes, the way how I defined them, they were defined up to order 1 terms, and I didn't specify the order 1 term. So here's the conjecture. There exists a unique formal power series which extends this semi-classical definition. It's this one. So now, before that was O of H, so now it's a formal power series in H, such that the corresponding transition amplitudes, they actually satisfy the semi-group property in all orders. And of course, this semi-group property, it's a very natural property that, we have the transition from one basis to the other, to the third basis, and it's the same as the composition. So the composition of this will give the transition from the first basis to the third basis. So the goal of these lectures is to argue that the conjecture is true, and it's not just true, but there is a beautiful answer for this, that these coefficients un are given by the sum of Feynman diagrams for the Poisson sigma model, for our symplectic manifold, with some special boundary conditions. Okay, so let's start with quantum mechanics, with the path integral for quantum mechanics. So if we have Dirichlet boundary conditions, the standard Feynman's formula for the propagator, for the kernel of the propagator in terms of path integral is just the following. We have to integrate in some slightly mysterious sense this function over the space of path with which originate at q prime and end at q, and this is t. So this, I mean, I think Feynman did it in the configuration space, but this is some natural counterpart which many people studied, the path integral in the phase space. Okay, so in a similar way we can change boundary conditions in the path integral, which would correspond to changing the matrix elements of the propagator. So before we used the Dirichlet boundary conditions, and the propagator was given in the as an integral operator in Q. So before taking the semi-classical limit, what's written here is the integral psi 2 b2 q ut q q prime. That's the propagator that I discussed before, and then b1 1 q prime dq dq prime. Okay, but now so what's the difference? So the difference now is that we have different boundary conditions. The boundary conditions now that the initial point should belong to this Lagrangian submanifold. When we say that gamma 0, in the previous case, gamma 0, sorry, I mixed up phase space. It should be pq prime, and p prime is any. In other words, gamma 0 should belong to t star q prime q, and gamma t should belong to t star q q. So that was before, and this is now. So the price for this changing boundary conditions, if we want to have the correct path integral, we have to introduce these boundary terms in the action functional. Okay, so now these are our paths. So this is, we integrate over this path. Gamma 1 and gamma 2 are paths that connect the endpoints of gamma 2 fixed intersection point A of these two Lagrangians. And to lighten all these computations, we assume that the intersection consists just from one point for the time being. Okay, so then what's the difference in topological quantum mechanics? In topological quantum mechanics, the Hamiltonian is 0. For the topological quantum mechanics, we have this expression. If we believe in path integral, then we would write something like this. Of course, so far, neither integration nor the space of path doesn't make sense. This is just kind of the symbol of the faith. So we want to have something like this. And of course, the way how we will proceed is we will define this integral in a formal way, where we don't really have to integrate, but where we will just have to differentiate. Remember that the definition of the formal asymptotical integral is such that in this integral you never see the integral itself. It's a formal power series in H, where in each order you have some differential operator acting on the integrand. So we will define this integral exactly in the same way as formal integral. There is an enormous literature on the definition of path integrals in the analytical way, and in some cases it's a beautiful analysis, and it's known as constructive field theory. You can, it goes back to probability theory, to Wiener integrals. There is a class of integrals like this that can be defined. Unfortunately, these oscillatory integrals, they fell into completely different, well, almost completely different setup. So this is the reason why we want to define them as just formal for the time being. And there is nothing wrong with this, in the sense that, well, it's a long philosophical story, but this is what we will do. We'll focus on formal definition. So, okay, so there is one big difference between this integral and the integral with the non-zero Hamiltonian, because here we integrate over non-parameterized path. So this reparameterization can be regarded as gauge invariance, and in this sense this integral is like a mini gauge theory, so it's a bit more involved. So let's turn the page. So now if we want to find critical points, we just have to vary this exponent, and the first term in the exponent is this integral. If we vary it, you will get this is the bulk term, and this is the boundary term. So for the bulk term omega, so you see this omega is d alpha. It's not, by the assumption it's non-degenerate, it's because we have a symplectic manifold. So that means that Euler-Lagrange equations are dx dt is 0, which means that x is constant, but we know that x0 should belong to one Lagrangian, x1 should belong to the other Lagrangian, which means that intersection points are exactly solutions to our Euler-Lagrange equations. But remember that in the variation of this term there are also these boundary contributions. And this is exactly why we have these integrals over gamma 1 and gamma 2. The variation of these integrals, so it's like this. We have L1, and then the path gamma goes away from here. Let's say that this is gamma 0. So when we vary gamma, this point varies, and that gives this contributions from the integrals over gamma 1 and gamma 2, and they cancel the boundary terms over there. And so intersection points of L1 and L2 are exactly critical points of the exponent. So, and if you look at the resulting exponents from this computation, you will see that they exactly match the exponents in A. And so we have a natural conjecture that actually this path integral, if we will be able to define it formally, perturbatively, as h goes to 0, it will be exactly the expression A. And that's what we will discuss in the next lectures.